Hello, everyone. This is Team Waluigi Lovers 2398729. My name is Pranav.
I'm Bhargav.
I'm Nick.
I'm Celine.
I'm Mindy.
And I'm Isita. Today we will be presenting on our final project utilizing the invaluable instruction and mentorship from our instructors and TAs. Each component of our final portfolio involves intersecting CS techniques with music. As music is such an important and fun aspect of all our lives, we thought it would be the perfect field to blend with computers, another fun and important aspect of all our lives. So let the symphony commence. Our first project focused on utilizing a convolutional neural network, a popular type of machine learning model that is extremely good at finding patterns between images, to determine which musical instruments were present in a given audio. Musical pieces from the Hermas dataset compiled by UPF Barcelona were used for analysis. With over 6,000 seconds-long clips, our convolutional neural network was trained to classify audio into 11 different instruments based on the patterns found in the spectrograms, which are a visual method of representing audio files using frequencies. We took inspiration from previous research done in classifying instrument sound with the Hermas dataset by Dominic King and Connor Settle from the Stanford University Department of Computer Science. Though our convolutional neural network structure was similar to theirs, we utilized the Python mygrad library introduced to us by CogWorks, as well as other processing insights from the program for this project.
For our machine learning model, our team chose to use a convolutional neural network. This is a type of neural network that has special layers called convolutions in its structure, where a filter is applied to an input data point that results in some features being activated. The input layer collects input data, which in the case of the convolutional neural network would be pixel information. Hidden layers extract patterns that cannot be observed by humans, aiding in increasingly accurate predictions as the neural network learns from more training data. The output layer returns probabilities for each of the different classifications possible in the model, with the highest probability being its official answer. This network did its best to identify features of our spectrograms, allowing it to learn which graphs correspond to which instruments and give us a prediction based on its learning. After the model trained, the training accuracy came out to be about 95%, while receiving a test accuracy of 75%. This clearly shows signs of overfitting, which is another word for when a model seems to be performing well at training, but actually does poorly at testing. Here's a short clip demoing our model in action.
Along with exploring the different models and tuning hyperparameters further to increase the accuracy, one future extension of this project that can and should be explored is the classification of non-European instruments, so that instrumental music from all over the world is studied and preserved in the form of digital data.
So a critical part of all audio analysis is the Fourier transform, which is a mathematical principle by which any closed function can be perfectly recreated as a sum of sinusoids. We decided to have a little bit of fun with this by taking a graph of the Dow Jones Industrial Average from 1900 to the present day, breaking into chunks, then decomposing these chunks into their most prominent frequencies, and then playing that back through the speakers as a sequence of pure tones. So we can see that in action right here.
Our genre classification project uses a convolutional neural network to analyze a piece of music and output a probability distribution among 9 genres, these being blues, classical, country, disco, hip-hop, metal, pop, reggae, and rock. This project was inspired by Kunal Vidya's article on Towards Data Science regarding his genre classification model. Our 9 genre categories originally came from the Jiqi-Zan dataset, which has been widely used in machine learning projects concerning music genre recognition. The dataset consists of 1,030-second WAV files, each containing a clip of audio corresponding to one of 10 different genres. In both our project and Kunal Vaidya's project, from which we took inspiration from, only 9 of the 10 genres were used due to an issue with processing jazz music files. We pre-processed our data by splitting each audio file into 5-second long clips to increase the size of our dataset and to train our model to be able to recognize genres with shorter clips of audio. After splitting each clip, we generated MEL spectrograms for each audio sample. A MEL spectrogram plots the frequencies at different times of audio samples on a scale that is normalized to how humans perceive sound. Since differences between higher frequencies are more difficult for humans to detect than differences between low frequencies, a MEL spectrogram plots sounds based on a logarithmic scale. MEL spectrograms were saved as NumPy arrays, representing decibel units and stored in respective directories for input for a model. In our project, we used a convolutional neural network.
We had both an implementation of the CNN that used Keras, which was what the Towards Data Science article used, and one that we built with PyTorch. Both models made use of 3 convolutional layers to analyze the image data of each spectrogram, and also a dense layer to have the model output a list of probabilities for how likely the audio fits into each genre. The final version of this project uses the Keras implementation, since our data processing and query functions were originally based around it. But our PyTorch version trains similarly as well as seen in this slide, and the query functions can be easily adapted.
Even though we resulted in a training accuracy of 60% on PyTorch and 70% on Keras, one of the ongoing issues we faced in both of our model versions was overfitting. Essentially, our model was learning specific quirks in the training data that couldn't be generalized to our testing or validation data. And we dealt with this problem partially by reducing our model complexity and the number of layers from 5 to 3. We also created a dropout layer which randomly set input units to 0 with a frequency of 0.3 at each step of training. Both of these changes made positive impacts on overfitting, but if we extended this project further, we would likely look into the dataset's impact on overfitting, as it was made between 2000 and 2001 and may have more narrow or outdated music samples. We trained our model using a batch size of 100 and epoch count of 25, and both of those parameters were calculated through trial and error over time. Now, using a query function, we were able to input audio files and view a corresponding genre probability distribution. Even with overfitting on our model, you'll see that our genre classification program accurately dissects the different styles of music in an audio sample. For example, testing disco, pop, country, and classical songs all returned accurate results. And since we omitted the jazz genre from our project, jazz songs generally had a higher probability of being the blues, since both styles are inherently related. Moving forward, there are definitely some functions to fix and features to add. We would want to experiment more with resolving overfitting and adding audio sampling and song name recognition functions to enhance our genre classification program.
So in another small project, we used an n-gram probability model to generate a sequence of notes based on probabilities generated from data it is analyzed. So this normalized function down here will take in counts of occurrences of notes and use it to associate notes with their probability of occurring, which we can see in this sorted graph down here. Down here, this function is going to act as our trainable model and keep a record of a history of a specified number of notes and keep track of how many times a certain note follows that history in our training data. And then it makes use of the normalized function to associate each history with a list of probabilities for the next note. And now we can just generate a random note, keep track of the history of what's being generated, and use the corresponding probability to select the next note for how many ever notes we want to generate. After trade on a few songs from A minor,
And for our last project, we decided to pay homage to Waluigi, our team mascot, by utilizing Python to transform simple piano pieces into melodies with the Waluigi wah sound as the instrument. With the help of the MIT Music 21 library and the Librosa library, we were able to convert MIDI files of simple piano pieces to repeat the same pitches in the wah sound effect. Here are short clips of fur release and hot cross buns in the instrument of wah.
So here I'll be quickly showing you what fur release in wah sounds like. And here to show the differences in beat length is hot cross buns.
Thank you so much for listening to our presentation. We are grateful to BWSI CogWorks for giving us the opportunity to learn so much about computer science and the chance to apply it in such an amazing way. The course itself gave us such an in-depth knowledge about techniques in many different areas of computer science, and the speakers of the BWSI seminars truly inspired us to keep exploring our passions. Please let us know if you have any questions about our work.